everyone was able to display in sagittal coronal, right? And you can change the slices and you could plot the time series, all of you. Hmm? What happened? Oh, okay, but you were able to do, right? Is there anyone who was not able to do? You can do. Okay. Um, all right. Um, so one of the problems with Google Colab is that, you know, once we have something, you will have to, let's say we finish something today, then if you are to run tomorrow, then you have to redo like all the steps. I'm trying to I'm trying to find out how, if there are ways to um, make it. If I can, then I will let you know before the course is over, right? So this one reads the data, and can anyone tell what these numbers are? Like 18, 8, 3, dot, dot, dot. So that is the, like any image is simply a matrices of numbers, right? So this is displaying the numbers across each row or column. Right, and then it displays, if we wanted to do, let's say, slice number 0, 50, 100, and 150, then we just need to run this and it will show, right? If we wanted to do for the other dimension, right? Is this okay? Right, so this is what you will get. So this one um, is sagittal or coronal. What kind of image is this? Is this way or this way? So this one is sagittal, right? Now, to do coronal, what is the command? Maybe someone could tell me. Colon, comma, Z. Is this going to work? Okay, so these are coronal, right? Okay, now this is the anatomical, this is to rotate. Someone had asked this question about, this is rotate 90. Did anyone try any other angle? Yeah. Okay. But did anyone try like 135? I think the trouble with rotating it at an angle other than um, multiples of 90 is that the matrix dimension changes, right? So you have to correct for that to do that. Okay. So now, let me see. Yeah. What happened? Right. It is the way it's displayed, but you can change for other values. Right, right. So sometimes we try to have like an index, but I don't think it is, for this one, it is necessary. Right, to, right. So it's like, okay, so like K is multiples of 90. Okay. Mm, okay, right, right, okay. Okay, so I guess, yeah. Um, okay, so, okay, so, mm, so this one is, okay. So this one is im show functional data colon comma colon. Um, rotate. So if we want to display it as a time series, then perhaps we can. mm, Okay, maybe this is not needed, right? Im show functional data and then colon. So instead of colon comma colon, which will display the images, we wanted 32 comma 32 comma I think 16, then comma colon. Okay, will this work? Does it look okay? Does it look okay? Like just any random coordinate. Okay. Funk M show 32. Do you know where I'm making a mistake? Maybe this. Actually, I can just let's see. I can delete. Mm, this one.
Okay. Then this IM show should be PLT dot plot.
PLT.plot. Okay. Okay. Thank you. All right. So now for any given voxel, we can plot. So this is one value we can basically, this is from the image. It's a little worrisome because it would suggest that there is a slow increase, right? So what we could do is change the slice and see what is happening. Okay. Okay, so it shows like in the center there is this slow drift which is present. We can try some other voxels also, maybe 30. Okay. Okay, so this is one way in which you can look at the different coordinates and plot it, right? Uh, hmm? What is on the y-axis? Good. So what is on the x-axis? Time points, because there are 818. So this is also 818 time points. So the y-axis is the bold signal intensity, right? So if we, let's say, go to the first, like the edge, the first voxel, it should be, any guesses what the signal should look like? Right? because like it's on the edge and we have removed some of the voxels. The other thing we can do is change, like go closer, right? This is still out. My guess is it would be outside. So this is like the scanner noise, okay? So that is, there is signal, but it's noisy, right? So this is from outside the brain. This one, I would guess it's still outside the brain, right? Based on the intensity, the y-axis. Like see the y-axis, these values are between 5 and 25. If something is within the brain, the magnitude typically is much higher, right? It's like 500, okay? So that is like, that's what I was saying, that the noise inside the brain is much higher than noise outside the brain, right? Because the noise inside the brain is both physiological as well as electronics, while outside it is simply just electronics, and that noise is much less. Okay. All right. So, okay, this is done. This is done. Okay. Control Shift plus. Is this better? Okay. Right. Okay, so it read through subject 1, MSC 1, and then we are doing brain extraction. So you can, again, try to be up to date so we can look at specific things, right? So this is just displaying the anatomical, right? Um, Without doing any um, segmentation, which would remove everything outside the brain, including the skull. right? So this is anatomical on the anatomical. So it shows a very good segmentation that only the brain, uh, only voxels within the brain have survived. Everything outside has been removed, right? So this shows how like the different parameters for doing the segmentation are different ways to threshold. But I have used the ones that we typically use. Right, so then is the motion correction parameter. In FSL, it's called McFlirt, motion correction using linear, linear image registration tool, right? And so does anyone know how motion correction works? Yeah, you use DTI, right? You don't use motion. Okay. Okay, all right. So the way motion correction works is that you have a 3D plus time data. You take typically one of the first images, like data set number one, and then do a linear registration with data number two and adjust so that data number two matches with data one. Then you do for number three with one, number four with one, and do it for, in this case, all the 818 images, right? And so that is for the functional data set, right? So in this case, it's a linear or a affine transformation. So that is why it is fairly quick, okay? Yeah, yeah. No, you can, but you have to, you cannot use the parameters I have used here, right? Because in DTI, in here, maybe the analogy is there is an object and you have taken pictures while the object has moved, but everything else has remained the same, right? And so the only thing where there is a change is the object moving. In DTI, there is a change in intensity, right? So in that case, you're taking a photo as the brightness is changing, right? And then you have to do motion correction. So it's not as straightforward. So it's a little more complicated. Right. Right. So, so that is where you can use. So for most resting state data, using a linear correction will work. But there are some cases, let's say someone, question? Okay. So if a subject was given anesthesia, then you have to be more careful, right? Because with anesthesia, you're changing the blood supply to the brain and the signal intensity may change. So simply doing this may not work. So you have to be careful. So this is like the mean changes. So there is not much change in here, right? So that's the variance image that is plotted. And so whatever is along the edges are here, right? So that is where most of the difference is. Then, we want to visualize the motion parameters, see how these changes look like. And these are the changes across translation and rotation, right? And as we discussed yesterday, because the translation is like fairly small, like 0.15 at most, so the subject did not move much, right? And similarly for rotation, right? I should say that this would, like, we would consider this like, because even if someone tried, it's very hard to move less than zero point 0.1, right? Um, yeah, right. So this is another way of estimating the motion. It is called frame-wise displacement. In frame-wise displacement, you are taking, like, instead of the 6 parameters, you are just using one parameter to get a aggregate information about head motion. So this is the frame-wise displacement, right, of 0.2. And this one tells you how many voxels or how many time points have, greater than 0.5, how many have greater than 0.2, and so on. So the motion parameter on this subject is very good. Again, these are the different motion parameters that you can try, right? So basically, McFlirt uses an optimization approach to find the best linear transformation that aligns a source image to target image. It typically works by calculating a similarity measure between the source and target image. It can be correlation ratio, mutual information, and then iteratively adjusting the transformation parameter, the translation rotation, to maximize the similarity measure, applying the estimated transformation to the source image to create a registered output image, right? So that is, like, as I said, it does this iteratively. And the good thing with brain imaging is that we can assume that nothing happens to the shape of the brain. Like, if we were to image, let's say, heart or lung, then these methods won't work because the shape changes, and because this is inside the skull, these changes won't occur, right? So this is for the functional data. The next is we will do a registration between the anatomical and the functional, right? So first, we make sure that the functional data is good, right? There is not much motion. Then we compare it with the anatomical data, right? With the mean functional data with the anatomical data, and then do whatever registration is needed. This process is called registration, such that between two images, either in time, right, either in time or between different images, they are fully aligned, so that I could, if I clicked on one brain region, then for the other image, it would be the same. So as I had mentioned yesterday, um, to compare different brains, we use a template, right? So any data which is used is transformed into this atlas called the MNI atlas. And by doing this, the advantage we have is that every brain is transformed into this. So by looking at your data, I can tell which location and where you are, right? So this basically performs. So we first do the registration for functional, then we do registration between anatomical and functional. Now we are transforming between anatomical and MNI. This is, I would say, this is not registration, but more of a transformation, right? Because it's like, let's say, we took one of your faces as a standard face, right? And then everyone's face has to be basically stretched or shrunk to fit the standard face, right? So we are doing the same thing here. Any questions? I think there's still a couple of minutes, so anyone has any questions? Yeah. Right. This one? Yeah, so this is displaying the, it's called frame-wise displacement for 100 images, right? And this one is motion correction, again for 100. It, no, yeah, so volume typically means data points in time, in time, right? So this one is, no, no. Right, right. So volume means the number of data points. So this data has 818 data points. So it has 818 volumes. Is that clear? Volume is, so the dimension was 64 by 64 by 36 by 818. So this is like 64 by 64 by 36 is one volume. The next time point is 64 by 64. Yeah. So, so like, unfortunately, there are all these technical jargons which is used. Volume is the same as number of data points. Mm, okay, right. So this is anatomical image on the MNI template. So this is, we have transformed the anatomical image to the MNI template, right? So we have used a affine transformation to match this. Can anyone tell what is the limitation of this? Does this method have any limitation? The, right. So maybe in terms, if I understand you correctly, what you're saying is that, let's say this was done using Caucasian brain, maybe using people from India, the template may not be the best one to use, right? Or if you were to scan 100 people in Japan, maybe this is not the best template. But that's a very good point. Are there any other limitation? Okay. Mm, something more straightforward, right? So let's say we were talking about autism, right? And let's say the age range I'm studying is between 5 and 8. Should I be using this to transform people's, like, kids' brain, right? Maybe not a good idea, right? So depends on, like, this is for healthy adults, right? Which should be used. If you were doing, let's say, older subject, it is still valid. You can still use, but if it was for a clinical group, right, um, then may not be valid, right? If I was scanning people with schizophrenia, right? People with schizophrenia typically have large ventricles, right? Then may not may not be valid. Okay. Yeah, yeah, yeah. For registration, right? Yeah. Which Parkinson's? Okay. Um, any, so maybe can you describe how does the Parkinson's brain look like, in case people don't know? Right. Right. Okay. Right. So if you don't think there is a difference in the structural image, then it is okay to use. What I was thinking was more simple. Let's say you had done a fMRI on a patient with a brain tumor, right? So there's a brain, like there's a blob somewhere here with high intensity. Now, if you're doing a transformation, that is going to provide a solution which is not optimal and may misregister it more even, right? So in clinical cases, you just have to be careful. Okay, so this is done. So this is, again, this shows that there's a good correspondence. And then you can, when you plot the contours on the anatomical image, this also looks good, right? So this is like what we call quality check, right? These are things we call quality check. So by the way, if I see any of you uh, dozing off, I'll take photos and post it on the web. Okay. All right. Um, uh, yeah, so that's the contour, right? So the MNI is image. So this is the MNI template, right? So the contour of this one would be, right? And then some here. For this one, it would be like that also. And so what we are doing now is that after we do the registration, like this one is good, right? This looks fine, but it's a little hard to say whether it did a good job or not, right? So like maybe visually a little easier is to plot the contour of one on the other, right? To see how it looks like. Okay. So once this is done, um, then what we do is we transform um, the functional using the anatomical image, right? So we are using the same transformation to MNI, right? Apply the linear transformation anatomical to MNI to functional. Yes. Right. Yeah. Yeah. Right. Yeah. So then you have to decide, right? If I was to do a motor task and somehow the registration is not good, then maybe, when you look at the data, you have to be very, like, you have to carefully make sure that they are aligned, right? So this gives us like an idea. Again, like all this is, you have the script, no need to, okay. So in here, what we do is um, we use the transformation, right? The affine transformation, which was obtained when we transformed the anatomical to the MNI template and use it on the functional data. Why is that? Why don't we take the functional data and then use um, linear transformation on the MNI template? Very good. Excellent. Um, because the anatomical details are less, also the matrix dimension are different. And because anatomical and functional have been already registered, so we simply transform it. Yeah, right. Right. Okay, okay, that's a good, again, I appreciate you asking. So this tells us that this is the, you know, MNI template contours overlaid on my functional data, right? Now, where I would become, so let's say I found some activation here on the edge of the brain. Should I take it as activation or not? But we have already corrected for motion. Speak up. So the CSF and other things have already been corrected. Let's assume that it has been corrected for. What would it mean? Hmm? We can take, okay, Joshua. Um, no, this is still anatomy, right? Someone else? How about you? Okay, so if you have some activation, let's say here, right, outside the contour, I would be careful, right? I would not, I would say it's very unlikely that this is real activation, right? It may be just specific to one or two subject, right? If you're doing whole brain across many subject, it is very, like, it's highly unlikely that you would see something. But if you see, then go through like on a subject wise basis, and if you still find, then what you should do is not use the MNI template, right? So let's say you saw, let again, let's say you saw activation um, someplace like here, right? Okay, maybe, yeah, let's say something around here you saw activation, right? Then it's very unlikely that it would be from from the subject pertaining to a specific task. All right. Also, there are, like, I'm not going, I don't think we'll have time, but so there are both linear and nonlinear warping schemes for MNI space. I typically like to use linear because, back and forth is fairly straightforward. The nonlinear warping can also be done, but it is more computationally expensive and it's no longer a affine transformation. So going back and forth um, is not easy, right? And also it's not very easy to explain what it did, right? Maybe it's like deep learning. It does, you get good results, but if you ask like if how it did or what it did, it's not so clear. All right. So the next step is to create a task design signal, right? So for the task design signal, we have task stimuli where in this case, very specific instruction was given to subject to do specific things, right? And what we are hoping is that when they performed those tasks, there was corresponding signal changes, right? Um, so in this case, we are going to use the motor task that was used, right? And they had 4 different tasks, like right hand, like right foot, left foot, and tongue, right? So they wanted to activate the whole homunculus, right? All the sensory motor region, and not just pertaining to the um, finger tapping. And so the TSV file that was provided has that information, right? So the TSV type has onset from 8.8 to 15.4, right hand. For the second task, 24.2 to 15.4, right foot, 55, 15.4, left foot, 70.4, duration 15.4, tongue, and then left hand, right? So each duration is 15.4 second. And right, so this is the duration. So we have to come up with a reference function. And we are going to use a hemodynamic response function, right, which starts with a small initial dip, although the dip is not always observed, or I should say very rarely observed. And then it rises to a peak after several seconds. It may take 4 to 8 seconds, and then returns to baseline. And then, as I had mentioned, there is a post undershoot, right? It goes below the baseline and slowly comes back to baseline. And for GLM, we have to generate a task design. Right, so here we are generating this. So this is the task design, right? So this is the different condition, like left foot, left hand, right foot, right hand, and tongue, right? So those are the 5 conditions. like left foot, left hand, right foot, right hand, and tongue. And then we have rotation. Right, I think it should be, um, there should be six. There should be six. I think it's just written in that way. Yeah. So 5, then these are the 6 parameters. And then we assume that there are drifts, right? And then there is a constant, right? So this is how it looks. So then, as I had mentioned, like in regression, you have y equal to alpha x plus epsilon, which represents the error. And okay, right. So again, with nylon, there is the GLM analysis that can be done. And this is the slice time reference. Again, so the slice time references, remember I had mentioned how when the data is collected, it is typically 1, 3, 5, 7, 9, 11, like it's called interleaved, and it's 2, 4, 6, right? So between the first slice and the second slice, there can be a delay of 1 second, right? So to minimize that, you can do slice timing correction, right? And so like the slice timing, and then you can use noise model instead of white Gaussian noise. You can also assume that the noise is autoregressive. Does anyone know what autoregressive noise is? Joshua? I heard from 2 people you're the smartest person in the class. No, pre-whitening, right? So what is autocorrelate, autoregressive? Did you say? Um, auto, autoregressive means that the current value is dependent on the past value, right? It doesn't have to be wholly dependent. It could be like xi equal to like random noise plus alpha xi minus 1, right? So the alpha is how much dependence you have. It could, if it is, let's say, 0.1, then like a small amount, but if it's 1, then it has a much bigger effect, right? So why do we take autoregressive noise model? Because the signal that we get are physiological in nature, and we have heart rate, respiration, and other signal sources which are autoregressive, right? So that is why we use this. But you can try other ones also, right? So that is done. Now we are to build the contrast, and then is the visualization, right? So this is how the results look like. This is left hand versus baseline. right? And so I guess many of you may know, like when you tap your left hand, the right cortex lights up, and when you type right hand, the left cortex lights up. So this one is left hand. So you see activation in the right cortex. Okay. Isn't this like magic? You collect someone and collect the data, you can analyze, you can tell so many things, right? Um, and this is a single subject, right? And maybe I should say that before fMRI, like there was no way, there was absolutely no way to get this information. And the only way you could was if someone was having had a tumor and you had to operate on, then you would cut open the skull and then probe them. The other way to do was to study monkeys, right? And you would train them and then, you know, basically train them to, let's say, move their left hand. And then when they move their left hand, you would give them some juice, right? And after that, you would drill holes in in the skull and put electrodes and then measure the electrophysiology. Um, right. Maybe when you are my age, everyone will have their own portable MRI. Okay, so right, so here what we can see is the red is positive change and the blue is negative change, right? Huh? So in that case, there is a positive change. The percent is positive. In the red, in the blue, the percent is negative. Like in those regions, compared to baseline, the signal goes down. For blue, for red, in those regions, the signal goes up. Anyone has any questions? Yeah, right, right, right. So the design matrix had baseline, 1 second. So like, so, so the blank regions, right, would be baseline regions, right? Like these regions are baseline, right? And then we could also take other regions, like this is baseline also, right? Like this region between 80 and 90, 80 and 90, right? This is scan number, right? So the scanning started from this time point and went first at 7, like I forget, like 12 or something. They had to tap their right hand for 17, right? And then they had to tap their right foot, right? And then they did left foot, right? So what we are looking for is left hand. So this would be baseline, this would be active, and then we can um, do like that, right? So this is left hand versus baseline. So then the next is to do right hand, right? So this is the right hand, right? So if you look, mm, do you see any pattern between left and right, right? So this is left hand. Look at like, watch, like, look at these figures, right? And then, right, look at the right hand. Do you observe anything odd in these figures? Yeah, very good. So in this case, so right hand activates mostly the left, but you also see some voxels from the right hand which gets activated. And the reason is that, you know, um, have you ever observed a little kid playing, right? Infant, right? They generally move both their hands in synchrony. So initially, they're all organized as one, and slowly with development, right hand can act differently than left hand, but there is some inhibition. That is, when you perform something in left hand, you have to inhibit the right hand from doing the same thing, right? And this is like inhibition, right? Okay, right. And that is how, like we had discussed, like as Rahul had mentioned, um, between left. So now you know, if you were to design a study to study between left-handers and right-handers, what would you expect to see? Huh? Right. Yeah. Right. Okay. All right. So, any questions? Yeah. Um, y- right. But it's not as dominant, so only a small portion. Only a small portion. So so this is activated, right? Because this is right hand finger tapping. So what I'm saying is some of these that you see is perhaps due to inhibition, right? Yeah. Uh, inhibition in a sense, inhibition in a sense that not excitatory and inhibitory. No, what I mean is that movement, like yeah, you are stopping yourself from, right? You were saying something. Yeah. Oh, this is not resting state at all. The resting state is maybe, so we'll cover tomorrow. So now, so now we should know how the sensory motor cortex is organized. How are the different functional regions in the in the task activation, right? And then you have to do all this task, all this tapping to activate. With resting state, even just by resting, we can generate the same things, right? Resting is, yeah, yeah, right, 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 made. Can you, I didn't understand your question. Yeah. Right. Right. Yeah. Right. 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 Uh, yeah, so typically what is done is that if you're doing the task for all the subjects, you would design in the same order or you randomize it in a very specific way so that, then you can do. Yeah, it would not be very, it would be um, very difficult to order it differently for each subject. So it's done across group. So now we can look at difference between right hand and left hand versus baseline, right? So you can identify these. So this is in case. So this, anyone know what this region is? Very good, cerebellum. So again, like with doing simple finger tapping, you can activate the cerebellum. Okay. So okay, right. So I changed the threshold value, right? So before it was 3, now I use 2, right? Which one would you use? So so which one gives better image? This one or what I just showed you before? Okay, so this one is with a threshold of 2. This one uses a slightly higher threshold. Okay, all of you remember this, okay? This is with threshold of 2. This is with threshold of 3. Which one would you use? Which one? 3? Um, let's say we made it 4. How would you argue with her? Any? But this one, but this looks so good, right? No, no, no. Okay, we are not looking at the baseline. Blue means negative, red means positive. Baseline versus, like condition 1 is baseline, condition 2 is right hand and left hand. Which one, what would be your threshold? Right. So what threshold would you use? What did you say? But no, no. Okay. Why do you say contrast? Like this is all activation. Red is positive, blue is negative, right? So this one looks good, right? Very distinct ones. And if I used, let's say, 2, so much more, right? So much more red voxel, so much more blue voxel. Which threshold would you use? But what is optimal? How do you know it is optimal? I have told you what my research question is. I want to find differences between which brain regions are associated with finger tapping. Yeah, so that's why I'm asking you, tell me the threshold. Right, right. The 3 will give, right? Okay, okay, okay. So those things you have to figure out, right? So that is the trade-off, right? So this one, as I reduce my threshold, I get more and more voxels. So tell me, what kind of error is this? Type 1 or type 2? So for this one, you think I have more type 1 error, right? Now, if I used, wow, such clear picture, right? So what do you think may have happened here? Huh? So maybe you have more type 2 error now, right? So you have like not many false positives, but what you may have done is threw away many voxels which were really active. Okay, so again, like this is one of the challenges in neuroimaging. If anyone can find a automated way that, okay, for this data set, this should be the optimal threshold, I'm pretty sure, and if people start following your paper, you can easily have many more citations than you can have. Like the paper would be cited like thousands of times. Yeah. Right. Uh, right. So you can, so if I understand correctly, if if we also had fMRI, in addition to fMRI, if we had PET imaging, and then you compared, maybe that would give, yeah, perhaps, but it's like, well, first of all, it's very messy, right? Like, you know, how many places can do PET and MRI, right? That is one. Then if you use EEG, it has its own headaches. If you do FNIRS, it's mostly superficial, right? So that is where I think fMRI is useful because, you know, it has decent spatial and temporal resolution, doesn't have any harmful effect, and you can do. So in to answer the question, there is something called ROC curve analysis. If I have time, I'll cover that. Looks at true detection versus false positive, and it comes up with a method. Okay. All right. So this is with threshold of 3. So when you give your presentation, you have to tell me how you determined your threshold, right? Okay, all right. So this is what we have so far. Um, so the next is spatial smoothing, right? Right. So here, what we have done is um, we have taken the data and smoothed the data using a 6 millimeter, right? Like we are using a spatial smoothing of 6 millimeter, and then uh, basically redoing the analysis, right? So we can display the data. This way, the data has more signal to noise ratio, but the problem with this data is that it has, what is the limitation of using spatial smoothing? Spatial specificity, right? So, right. So if you, if your data was collected at, let's say, just as an example, 2 by 2 by 2, and then you use a spatial smoothing of 6 millimeter, then the data, the resulting data may have more signal to noise ratio, but you cannot say that the spatial resolution is 2 by 2 by 2 because you have used a spatial smoothing of 6 millimeter, right? So you lose spatial resolution. Huh? Right. But if you use 2 millimeter, so let's, okay, so let's say, so you collect data at 2 millimeter by 2 millimeter, and then you say, I'm going to use a spatial smoothing of 2 millimeter. What does it mean? It's not doing any, it's not doing anything because you are smoothing just that voxel. All right. Okay, so everyone is clear with this? Okay. Huh? I, I I agree with you, right? Like, yeah, 6 millimeter may be too much, but by using 6 millimeter, what you're also doing is it's almost like doing clustering that I covered yesterday, right? So this is in some way clustering the data, right? So um, if there are some voxels somewhere around here, it will make it into a big blob of one cluster, right? While some random voxels which have passed the threshold would become in, like, they would not pass the threshold, right? So that would be another way to find clusters. Okay, did and yeah, this is without any statistics. So we are going to cover that later, right? So what I have done is for the first subject, right? Um, there's a couple of things you can do. Um, remember, the first subject had two motor runs, motor run 1 and motor run 2. So maybe in the next half hour, um, what you could do is one of two things, right? You could either So either use this data but do run 2, or do the second data and do run 1 also, and then show me show me the comparison between the two. Yeah. All right. So basically, you just have to repeat the steps, but try to understand what is being done. Yeah. Mhm. Yeah. Right. Right. Okay. Ir- Yes, you can do that. Um, you want me to show you now? Okay. time points, right? I just showed you what I did, and this is the dimension, right? So the two motor tasks are 104 time points. Um, I have to finish by 4 because I guess there is another class that Dr. Bhumika is going to teach to some of you. So I'll just stop here. So if you can do for another subject or another session would be good, right? And the design matrix like is 104 time points across 5 different conditions, and then 6 motion parameter and 4 drift and a constant, right? So that's how your design matrix should be. And I know it's a lot of work, but try to do for another subject or another run, and please send me the results like tonight, and then we can try. Then I think then it will be much more fun with resting stage, right? Where you can see how without any information you can generate.